well. Second thing, today is a bit of a special tutorial because we're going to go through the past exams, so the one from last year, term 3. So you can find it here, past exam, and it's the last one, final exam 2019, term 3. And today we'll do calculus. I hope that you've attended the algebra session. And please try to make it interactive, ask questions, use the chat, and yeah, we are 2 of us, so we can, we'll do our best to answer all your questions. That's all I have, so all yours. Let's start with question 1.
So I'll just be doing this on the board. Hopefully everyone can see me with the video and so on, with the camera. Just turn my camera on. And if you want to ask me a question in the middle of this, so either do it in the chat or just turn on your microphone. I should be able to hear you. All right, so let's start with problem 1A.
Wait, let me stop sharing.
Yes. So.
Okay, that's better.
Okay.
Okay.
Right. Okay. 1A asks us to do the following. So we want to evaluate this limit as x goes to 0. So sine x minus x over x cubed. All right. So that's the limit that we want to evaluate. Just copy this once more down here, and I'm taking x to 0. So whenever I'm taking x to some value, the first thing that I at least want to try is just to plug the number n for x and see what I get. Well, if I do that, I get sine of 0 minus 0 over 0. So that's 0 over 0, right? So in quotes, I do have 0 over 0. So that tells me I can apply L'Hopital's rule. And if I get some value after that application, then that whatever that limit is should be the same as this. So I apply L'Hopital's rule. So what that is I differentiate both the numerator and the denominator. And so if I differentiate the denominator, that's 6x squared. Ahead of myself, 2x squared, 3x squared. Upstairs, I get cosine x minus 1. Right? All right, so let's take a look at that. That's a new fraction now. So as I take x to 1, downstairs I still get 0. Upstairs I get cosine of 0, which is 1. 1 minus 1 is once again 0. So in quotes, I still have 0 over 0. So I apply L'Hopital's rule one more time. All right, so let's do that. Because whenever I have 0 over 0 or infinity over infinity, I can apply L'Hopital's rule. If I eventually get a limit, then the original thing, well, get a number as a limit, the original thing must be that same limit, must have that same limit. So differentiating the denominator, I get 6x. So upstairs, now I get a negative sine x. The minus 1, of course, goes away when I differentiate. All right, so now examining this, so x goes to 0, sine of 0 is once again 0, 6x is, well, that's still 0. As I take x to 0, so that's just 0 over 0 once again. So I can apply, or I should apply, L'Hopital's rule again, and that will give me a 6 downstairs, and upstairs I get a minus cosine. So now, if I take x to 0, I no longer have a 0 in the denominator, and upstairs I get a minus cosine of 0, which is 1. So this whole thing becomes minus 1/6. So since there's eventually a limit, a number, That means the original thing must have the same limit. So hence the limit as x goes to 0, sine x minus x over x cubed, that's -6. Right? So eventually I got to a number, a limit. That means the original limit must exist and must be that same number, -1/6. Right. So any questions here? All of this is being recorded, so you can obviously rewatch it if you want later. And of course, you can ask me questions in the chat when other problems are being gone over. All right. Okay. So that's all yours.
All right, so that was question 1. So I think the question 1A, that was worth 2 marks for last year's exam. But again, everything is going to be a bit different this year. All right, so I'm going to go through question 1B, which was worth 3 marks. And you'll understand why, because it's pretty long. Okay, so first we have an integral and they tell us what to do with it. So it looks pretty easy. So the idea here is to use integration by part twice to rewrite this integral, which is the integral of a product of 2 parts. So it all makes sense. So integration by parts. So I hope you all know this formula. Okay, so if we have the general one, if we have the integral of u times v dash dx, let's say it's between a and b, so we're going to look at the case for a definite in, then it's going to be the product of u and v between a and b minus another integral. And this time is going to be u dash times v dx. Okay, so just to recap, integration by part is not solving your integral, but you end up with another one. And the idea, hopefully, is that the second one is going to be easier. So the secret when using integration by part, in general, I'm going to write it like that, integration by part, is to choose which function is u, which function is v dash to start with. U is going to be differentiated to get a u dash, and v dash is going to be integrated to get a v. So usually there's an obvious way, there's a right way or a way, and one is obvious. But here we have an exponential and a cosine. So if we differentiate the exponential, we get an exponential. If we integrate an exponential, we get an exponential as well. So it doesn't really matter. And for the cos, if we integrated or differentiated, we end up with the sine. So you can see straight away that it's going to be hard to solve this integral. So, well, you just choose something and you try, because the question tells you try to use integration by part twice to evaluate this integral. And I would like you to answer the chat if anyone sees where this is going. Because as I said, if we use it once or twice, we'll still have an integral of exponential times a cosine. So yes, please, Andy, do you wanna?
Yes, ma'am. Just let me ask a question. When you said that you have to make each variable u and v, or u and v dash.
Yes.
How do you know which one to choose?
Exactly. Well, u is going to be differentiated, okay, because you end up with u dash, and v dash is going to be integrated. So it depends on the form of your integral. So if you have x times cosine, you choose x to be differentiated. So x is going to be u, because if you differentiate x, you get 1. And if you integrate cos, you get a sine. So your integral is going to be easier. So you need to think about it, or you just try and see if your integral is going to be easier or not.
Just one question. Does both ways work? I mean, if you chose
it
u
depends.
Okay.
It really depends. In this case, well, both way works because this is a bit special. We're not going to make it easier, the integral. But if you think about it, if you do it twice, the exponential is still going to be an exponential, and the cosine is going to be a sine and then a cosine. So you end up with the same thing. Okay, so yeah, let me, okay, I'm trying to read the chat at the same time. Yeah, nice. I think for this one, do it twice and get the 2 times integral and divide by the rest by 2. Yeah, something like that. So if we do it twice, we end up with the same integral. And then we have an expression with this integral, we can find it. Okay, so I'm going to start doing it. How do you know when to use U and flash? You try, you think about it. So in this case, we can use whichever because they're both of them end up with something similar when you integrate or differentiate. So let's make this one. So U is exponential, no, sorry, I say that U is cosine 3x, which means U dash is negative 3 sine of 3x. And V dash is, if V dash is exponential to x, then the primitive is going to be exponential to x on 2. Okay, so let's just do it. So I'm going to call it I, the integral. So integral between A and B, in 0 and pi. Okay, integral between 0 and pi of exponential to x cos of 3x dx. All right, let me do it and I'll check the chat later. So using the formula, I get U times V, so cos 3x. V is exponential to x on 2, okay, between 0 and pi, minus the integral between 0 and pi as well of U dash times V. So I'm going to put all the factors at the form. So minus minus is plus. I have 3 half sine of 3x exponential 2x dx. Okay, so again, you see that we end up with another integral, which is actually not easier to solve. But I'm going to give it a name. This is, say, I2. Okay. And they say you need to do integration by part twice. So let's do integration by part twice. So second one, for I2, I'm going to do the same thing. And again, you can choose, in this case, you can choose whichever you want. So I'm going to keep the same thing. So U is going to be the trig function, so sine 3x. And V dash is exponential to x. Okay, so I get that U dash is 3 times cosine 3x up, and V, well, still the same thing. The primitive is exponential to x on 2. So I2 was integral between 0 and pi of sine 3x exponential to x dx. Okay, I just apply my formula. U times V is sine 3x exponential 2x on x between 0 and pi minus, okay, and let's have a look at the factors. So it's minus, I'm going to have a 3 and a 2 here. So cos of 3x exponential 2x up, and that's where you see the beauty. And you see how you're going to end up solving this. Because this is actually the same thing as this. Okay, so this is our integral we had at the start. Okay, so this is actually just I. So let's finish this one. Okay, so here it's gonna give me sine of 3 pi up exponential 2 pi on 2 minus sine of 0 exponential 0 on 2 minus 3/2, and I say that this is my integral I called I to start with. And sine of 3 pi, sine of 0, it's all 0. So we get that my integral I2 is just negative 3/2 of the integral I. Okay, so now let's put everything together. Okay, so finally, if I go back here, I get that I equals, that was cos of 3 pi exponential 2 pi on 2 minus cos 0 exponential 0 on 2 plus 3/2 what I called I2, my second integral. Okay, cos 3 pi is negative 1, so negative exponential 2 pi on 2. Cos 0 is just 1, and exponential 0 is 1, so I get 1/2 plus 3/2 I2, and I'm gonna substitute I2, that was negative 3/2 I. Okay, that's just from here. Okay, and now I get an expression with I. So the idea, of course, is to factorize I. So on the left-hand side, I had 1. On the right-hand side, I had minus 9/4. So it's going to be a plus equals negative, well, you can factorize everything. So exponential 2 pi plus 1. And in the end, this is 4 plus 9 is 13. So I get 13I on 4 equals negative 1/2 exponential 2 pi plus 1. Which gives me in the end I equals negative, I can divide by 2, I get 2 on 13 exponential 2 pi plus 1. And done. Okay, is there another question about this problem? Yeah, exactly. So yeah, in this case, you can use both ways because you have an exponential and a cosine. So both the exponential and the cosine are gonna give you something similar if you integrate or differentiate them. Okay, any other question, please? All right, otherwise I will move on.
All right. So turn on my camera here, and we will look at problem 1C. So this is 1C. And it's got two parts. So part one is to state the mean value theorem. Value theorem. And And part 2 is some other problem, but let's deal with part 1 first. All right, so let's just write down the Miller theorem. You don't need to state it word for word in well, whatever you read in the notes. I mean, it's not. It doesn't need to be a complete quote or anything. It's just that you need to write down all the important ideas. So the real key is the following. So if f is a continuous function on a closed interval from a to b, and differentiable on an open interval, on the same open E interval, differentiable on the open interval from a to b. All right. Then the following will happen. So then there is a point C, that's in here, AB, such that the following happens. F of B minus f of A divided by B minus A is exactly the same as the derivative of f at C. So I mean, I'm sure you've seen this picture when you learn this theorem. So that's your A, that's your B, and you have some function that's differentiable on the open interval between A and B. Suppose you have such a function here. And if you take a look at this expression that's on the left-hand side of the conclusion of this theorem, so you got the change in the function values, change between the function values from A to B, and downstairs you have this B minus A. So basically you have the change in Y divided by the change in X. So that gives you a rate of change, right? That gives you a slope. So it's really the slope of the line segment connecting the endpoints of this curve. All right, so slope of that line, that's your left-hand side. Well, okay, your right-hand side, f prime of C. Well, we've understood what the left-hand side entails. The right-hand side, well, the derivative of a function and at a point gives you the slope of the tangent line at that point. So this equaling that means there is a point in this interval here whose derivative or whose the tangent line at that point has exactly the slope this, right? The rate of change over the whole interval. Well, from this picture, well, there may be more than one point here. So that could be a potential point for C, because the slope of the tangent line here is exactly the slope of the secant line going through f of A and f of B. So slope of the tangent line. That's your right-hand side. I mean, the most important part about this statement is the slope of this secant line, which cuts through the graph, right? And it connects the two endpoints of the graph, equals exactly the slope of the tangent line at some point in the interior of the interval. That's pretty much the most important part of this theorem. The conditions are obviously all important. The function needs to be differentiable on the interior of the interval, because otherwise f prime here doesn't make any sense. Continuity is of course important. You need continuity at the endpoints as well. So the function needs to be continuous on the closed interval and differentiable on the open interval. It doesn't have to be differentiable at the endpoints. And once you have that, then the secant line going through the endpoints of the graph, the slope of that should be exactly the same as the slope of the tangent line at some point in the interior of the interval. Right? And why is this useful? Well, part B or part 2 should illustrate the utility of this theorem. So, any questions here about the on the statement of the theorem? Well, I mean, the important thing is really just in this equality here, the slope of the secant line equals the slope of the tangent line at some point. All right, so that's part 1. So let's move on. Well, part 2, unsurprisingly, asks us to apply this theorem to solve some problem. So use the mean-value theorem to show that the following happens. So the cube root of 9 to the 1/3 power, is 2 plus epsilon with some epsilon. All right, so 0 less than epsilon less than 1/4. All right, so that's that. Well, let's brainstorm a little bit before starting. Well, okay, so the cube root of 9 is 2 plus something. Well, that something, that really defines this something, right? So epsilon here is really the difference between the cube root of 9 and 2, right? That defines epsilon. That's not so interesting yet, but probably the most interesting thing, well, the thing that you want to realize is the following. 2 is the cube root of 8. Well, okay. Yeah, so it will be true. You can certainly apply the mean-value theorem to show that epsilon is at least 1/9, and then most 1/12. But over here, this problem only asks you to show that epsilon is in this bigger interval from 0 to 1. Is it epsilon?
No, epsilon is between 0 and 1/12. There was another version, an earlier version of the exam, which has epsilon between 1/9 and 1/12, but that was wrong.
Okay. Right.
Yes.
Okay. All right. Okay. That's okay. Okay. Sure. Good. All right. So I'm glad that's taken care of. So epsilon is the difference between the cube root of 9 and the cube root of 8. Okay. So we have the cube root of 9 and the cube root of 8. Well, why is the mean-value theorem relevant? Well, if we recall, the most important part of the mean-value theorem is f of b minus f of a equals b minus a. That equals to something, right? F prime of c. So if you take a look at these two things, this looks like the difference between two function values, right? So the difference between if your function is the cube root function, that's the function value at 9, that's the function value at 8. Right? So I'm looking for the difference between two function values. And if you take a look at the mean-value theorem, on the left-hand side, you precisely have the, well, somewhere in this expression is the difference between two function values, right? So f of something minus f of something else divided by b minus a, that equals to something else. So just thinking along these lines, it seems that it should be relevant. Well, the mean-value theorem should be relevant here. If f is the cube root function, then upstairs I have f of something minus f of something else. that's precisely what I want to what I want to have bounds on, right? So okay, so let's do that. Let f of x be the cube root function. So epsilon here then is really just f of 9 minus f of 8. All right. So that's almost the what I have here for the mean value theorem, except it's only the numerator of the left-hand side. So let's move this to the that b of b minus a to the other side. So an alternative way of stating the mean value theorem is f of b minus f of a equals b minus a times f prime s c. Right? That's really the same thing. All right, so this should be the same as. Yeah, so go ahead.
I don't understand how then epsilon is equal to f9 minus f8.
Well, so f is the cube root function, right?
Yes, sir.
So f of 9, that's the cube root of 9, right?
All right, yep.
And f of 8, that's the cube root of 8.
All right, so you just, okay, yep. That makes sense. All right.
That's basically that's how epsilon is defined here.
All right, yep.
So it's f of 9 minus f of 8. By the mean value theorem, or rather a different way of stating the mean value theorem, that difference between the function values should be the same as the difference between the arguments. So 9 minus 8 multiplied by the derivative of the function at some point. That's between 8 and 9. Right? So f prime at c for some c that's inside, that's between 8 and 9. All right, that's just the application of the mean value theorem here. So let me just write that here. So that's what the mean value theorem tells us. Well, okay, let's clean that up a little. 9 minus 8, that's just 1, so f prime is c. So whatever this epsilon is, whatever the difference between the cube root of 9 and 2 is, it should equal exactly the derivative of this function at some point that's between 8 and 9. So that's what the mean value theorem tells us. All right, so then it's just a matter of figuring out what this f prime is. C, I don't know for sure. I mean, C is something that's between 8 and 9. I don't know exactly what it is, but once I figure out what f prime is, I should be able to say how large or how small this ever gets. Right, so f prime is c, f prime of x. If f is this, then f prime of x is, well, this is x to the 1/3, right? So that's 1/3, x to the negative 2/3. Or if you want, you can put it as 1/3, the cube root of x squared. All right, so that's what f prime is. And c is between 8 and 9. So let's see. That's f prime is c. Well, let me write it here. Farther out. F prime is c. Well, what is this? I have an expression for f prime of x, so let's just put c in. So it's 1/3. Then it's the cube root of c squared. Well, let's see, how large or how small is this number? Well, we we basically figured out that epsilon is basically f prime of c. And our goal is to show that epsilon is positive and less than 112. So then it basically is the same thing as saying this thing is larger than 0 and less than 112. If we can conclude that, that would be fine. Well, okay, so is this thing positive? Well, it's certainly positive because everything is positive here, right? So 1/3 times c is between 8 and 9. So c squared and the cube root, that's always positive. So this is certainly positive because c is positive. As c is positive. Well, c is not only positive, it's in fact always larger than 8. All right, so that's that. Is this thing less than 112? Well, let's take a look at that. So f prime of c is 1 over the 3 times the cube root of c squared. Well, let's see. How large is that? Well, how large can it possibly get? Well, this expression is the largest when c is the smallest that it can possibly be. C is in this interval from 8 to 9. So when c is at its smallest possible value, f prime of c is at its largest possible value, right? So when the denominator is as small as possible, then the whole thing is as big as possible, right? So this is certainly less than. C is at least 8, so I'll just put that in. That will certainly give me an upper bound. So 1/3. So the cube root of 8 squared. Well, 8 squared is 64, and take the cube root, that's 4. So it's 1 over 3 times 4, right? So that's 12. All right, so what do I have? Epsilon is the same as f prime of c for some c, that's between 8 and 9. I don't know exactly what it actually is, but I know it's at least 8 and at most 9. Epsilon is the same as f prime of c, and f prime of c, I have an expression. This 1 over 3 cube root of c squared, and c is positive, so everything here is positive, right? So f prime of c is positive, which means epsilon is positive. Then f prime of c, how large can I possibly get? Well, it's the largest possible when c is the smallest possible, right? When it gets to its smallest possible value. C is at least 8, so if I stick in 8 for c, this whole fraction, I'll have an upper bound for f prime of c. All right, and so if I stick in 8, just a quick computation will give me that it's 112. And so f prime of c is at least 0 and at most 112. And epsilon, as I've already computed earlier, that's so epsilon, therefore. Epsilon, well, in this computation, using the mean-value theorem, epsilon is the same as f prime of c, so epsilon is at least 0 and at most 112. And that's precisely what we want, right? The difference between the cube root of 9 and 2 is epsilon, and that epsilon is between 0 and 112, right? So we can lay that proof to rest, right? Any questions? All right, so.
Okay, so I just put a poll together to have an idea. Yeah, I agree. Well, yeah, let's see the response. You can remove the poll on your screen with the corner on the top right. Yes. And please ask questions. Okay, and I'm gonna prepare next one. So now we're gonna jump to yeah, Yes, Andy, go for it.
Yes, ma'am. With the question, it says use the mean value theorem to show that 9 to the power third equals 2 plus epsilon. What I thought was that we actually had to prove that and then use the range. So this equation here is just to help us show that the range is correct. Is that correct?
Well, actually, so the point of the problem is the following. This thing here, the cube root of 9 equals 2 plus epsilon. The point of that is, well, we know what this number is. We know what 2 is. I mean, this number is whatever it is. This thing gives you a definition of epsilon. This is to say that the difference between the cube root of 9 and 2 is epsilon. And you're asked to show, basically, if I'm to say this in words, you're asked to show the following. You're asked to show that the difference between the cube root of 9 and 2 is at least 0 and at most 1/12. That's how this problem should be
All right. Okay.
understood.
Right. So, yep. All right. Thank you, sir.
Sure. And any other questions? All right.
Okay, I have to say that I find this question hard as well. So the secret for the mean value theorem, and especially this one, is to find the right function. And here when you see the 9 to the power 1/3, you have a good idea that it could be f of x equals x to the power 1/3. And then to find the right interval, and then you just try it. But yeah, I agree with like the 32 of you saying that it was the hardest one. Integration by parts, it's just mechanical. So you can retrain and you'll get there. Okay, so I'm gonna move on. Okay, and stop the poll. Up. Okay, so moving on. So you have done question 2 in algebra. And now we're gonna move to question 3. Okay. So question 3 is, I'm pretty sure you could have solved it in high school. And the whole point here is not to solve it like you would have in high school. So we want you to be rigorous and to use the right theorems, the right assumptions, the right functions, etc. So, okay, so let's get it started. All right, so you have a string of length 1, okay, which is cut into 2 pieces of length x and 1 minus x. And then you use this string to do an equilateral triangle, okay, with one of the piece, the one with length x, and a circle, which has a circumference 1 minus x. Okay, and then you look at the total area of the 2 shapes. I don't really know why you would do that, if there's any application, but well, that's the idea here. So let me draw it first. Equilateral triangle, let's say that this is equilateral triangle. So we know that we use the length x to do this triangle. So each of the side has a length x on 3. Okay, and then we're gonna do a circle. So let's say this is a perfect circle, and we know that the circumference is 1 minus x, and the circumference of a circle is of course 2 pi r equal minus x, and r is here the radius. Okay, so we are interested in areas. So let's call this area A1, and the other one for the circle is going to be A2. Okay, so the total area of the 2 shapes is denoted A, so A equals A1 plus A2. Okay, and this is the area. Okay, and then we have a few outputs from Maple. So we have something for A. So this is going to be useful to check your answer. Okay, that's probably going to be what you find for the area. Then the derivative of a dA dx, and then x0 for which dA dx equals 0, and a of x0. Okay, so question I. By referring to the appropriate theorem, explain why there must be a maximum and a minimum total area A. Well, theorem and minimum is probably going to be the maximum minimum theorem. So I hope you remember it. The maximum minimum theorem is pretty simple, and it's all about continuity. So it says that if your function is continuous on a closed interval, then the function attains a global maximum and a global minimum. So we need a function, and which is going to be the area. We need to check that it's continuous and find the closed interval. So let's find this area. So let's have a look of A1. So area of the triangle A1. Okay, A1 is going to be 1/2 of base times height. So we need this up. Let's call this h, the height of the triangle. So we have this is x on 3. This here is going to be x on 6. Okay, and from Pythagoras, okay, we have that h square. Again, that's really high school. So it's going to be x on 3 squared minus x on 6 squared, which is x squared on 9 minus x squared on 36. You put everything on the same denominator, you find 4x squared minus x squared, so 3x squared on 36, which gives you h is positive, so square root of this, so square root of 3 times x divided by square root of 36 is x. Okay, and all of that is useful to find A1. Yeah, okay, that's true. If you find something else quicker, just use it. Can you just state the area since it is given in the maple session? Honestly, I would say no. That's fine, it's gonna take you not too long. So A1 is the area of the triangle, so 1/2 times x on 3 times square root of x, well, h. Okay, and you find x squared square root of on 3, and 6 times 3 times 2 is 36. Okay, let's just check. Yes, that works out. So this is the area of the triangle, then area of the circle. Okay. We have 2 pi r equals 1 minus x, so h equals pi r square. And r square, if you look up here, it's going to be 1 minus x squared divided by 2 pi squared. And you find 1 minus x squared minus 4 and pi. Check. Yeah, that works out. Okay, so in the end, your function, the total area, okay, so a is a function of x, is going to be x squared square root of 3 on 36 plus 1 minus x square on 4 pi, because it's a1 plus x2. Right, so now the important part is this function is just a polynomial, okay? You have x squared and another x squared, another power of x, so it's just a polynomial. So A is continuous, okay, everywhere on R, but do we actually care about R? Not really. So what is the domain of A? So values for x, with string of length 1, and then we have one piece of length x, one piece of length 1 minus x. Awesome. Oh, almost. So x is going to be between 0 and 1. Yes, exactly. 0 and 1 are possible as well. So we need to include the endpoints. Domain of A is 0, 1. Okay. So A is continuous on the closed interval 0, 1 because it's continuous everywhere because it's a polynomial. Which means that we can use the maximum minimum theorem. So by the maximum minimum theorem, which I'm going to write like that, max min theorem, theorem, we know that A attains a global max and min on this closed interval. Okay, so that's for question I. And question I was actually 2 marks, so it's not nothing. Is there another question for that? That was the easy part.
One question, ma'am.
Yes.
It's in the interval of 0 to 1 because the length of the string is 1, right?
Exactly. The length of the string is 1, and
Okay.
and then you have x and 1 minus x. So
Yep.
yes.
All right. So
All right. So question 2. Find the values. Well, the value of x that maximizes the total area and the value of x that minimizes the total area A, and give reasons. So again, here you need to use what we taught you because it's the right way to do it. So we know that the maximum and minimum points are on what? Anyone on the chat? What the maximum and minimum points are on something we call yeah, critical points. Awesome. Okay. So the max and min are on critical points. And we have 3 different types of critical points, which are, well, if we start with the easiest ones, endpoints. Okay, here the endpoints are 0 and 1. Okay, so that's an option. Then the other type of critical points is where the function is non-differentiable. So non-differentiable points. Well, let's have a look at our function again. A of x is here. Up. And it's continuous everywhere, and it's actually differentiable everywhere. Okay, it's just a polynomial. So there is no points where the function is not differentiable. So this is the empty space. Hope you've seen this notation. And the third option is stationary points. Stationary points. Okay, and these are points. For example, I'm going to call it C such that here it's A, so A dash of C equals 0. So it's where the derivative is 0. And that's where these outputs are going to be useful. If you look here, we have already Maple, which did the derivative of a for us. So dA dx, so that's dA dx. So we have the value, and here it's like a point C. So solve dA dx equals 0 for x means for this point x0, we have the derivative, which is 0. Okay, so that's our stationary point, right? So from Maple, we know that C is, well, what they call A0, x0, so 9 on square root of 3 pi plus 9. And we actually have, if you look now here, that's A of C. And A of C equals, well, I'm going to get rid of some of these digits, so 0.03 approximately. Okay, so let's have a look at the question again. Find the value now. So we need to find the values of x that maximizes and minimizes the total area. Okay, so we know that the max and min are going to be at critical points. Now we need to compare them to see which one is going to be the value of x for which we get the max, which one is going to be the one for which we get the min. So values of a at the critical points. Okay, so we need a of 0, a of 1, because these two were endpoints, and then a of c. A of c, we already have it from Maple. It's approximately 0.03. A of 0, let's have a look at a, which is, again, up here. A of 0 is going to give us 0 plus 0 plus 1 minus 0, so 1 on 1 squared on 4 pi. And here you need to take your calculator, and you find 0.08. And a of 1 is going to be square root of 3 on 36 plus 1 minus 1, and that gives you approximately 0.05. Okay, so you know that the max and the min are going to be one of the three. You compare, well, this is the biggest one, and the smallest one is the min. Okay, so to answer the question, we need to find the values of x for this max and min. Okay, so max for x equals 0 and min for x equals c, and c is, I guess you have it there, but you need to take your calculator and you find approximately 0. Well, yeah, you can just leave it like that too. So 9 on square root of 3 pi plus 9. Is there any question for that? Please remember to do it properly. So that was 2 marks as well. So when we mark it, like I want to see the critical points and I want to see the different values and the answers. Okay, question, the third question. Okay, so let's move it down there. Okay, so now for each of the extreme values you found in previous question, determine given reasons whether the circle or the triangle has largest area. Okay, so let's have a look. So the extreme values are the max and the min. Okay, so the max, that was for x equals 0, and we need to compare the area of a circle and the area of the triangle. So we actually need to go back up here. Oh, so it's going to be small. So area of the circle up and area. Okay, I'm just copying this here. That's what we had before. So the first one was triangle. So for x equals 0, well, we see straight away that A1, which was triangle, is going to be 0. Okay. So whether the circle or the triangle has the largest area, well, it's going to be the circle has the largest area because triangle has area equals 0. Okay, so if you want to maximize the total area, well, you just don't do the triangle, basically. If you want to minimize the total area, we found that that was for x equals c. Thank you. So for x equals c, well, we need to compare A1 and A2. A1, well, you take your calculator for x equals c, you find up 0.018 and A2, something like that. So A1 greater than A2. Okay, so the triangle has the largest area. Okay, and that's it. Is there any other question? So the third one was 2 mark as well. So again, this is pretty straightforward, this problem, but we just want to make sure you do it properly. So state which theorem you're using, make sure your function is continuous on the closed interval to use it. Then you list the critical points, you compare, and you the global max global. Okay, moving on.
We are moving on.
Oh, yes, didn't take a peek. Let me put it back up. Okay, you have 10 seconds to take a peek, Michael. Okay, yep, and done.
So this is all recorded. So if you didn't catch anything, you can always rewatch the recording. Anyway, so the problem asks us to apply the limit comparison test. To determine whether this integral, which we call j, from 1 to infinity, x square root of 1 plus x to the 4th dx, whether that converges or not. All right, so let's think about this. Well, so first of all, let's recall what the limit comparison test is for integrals. So limit comparison. So for integrals, well, when you compare, that means you have at least two functions, right? So f of x and g of x, you got two functions, and they're both positive and continuous. Okay. All right. So positive and continuous. Then, if the limit, as say x goes to infinity, f of x, let's say f of x and g of x, if that limit is some L, say, then well, with L, that's positive and finite. So if the ratio of two functions, as you take x to infinity, has a limit, and the limit is L, and this L is positive and finite, then the two integrals, well, this from a to infinity f of x dx, and interval from a to infinity g of x dx, they either converge or diverge together. Either both of them converge or both of them diverge, right? So either both converge or both diverge. So that's the statement, which continues on the bottom of the board. All right, so that's certainly relevant here because we're trying to determine whether this integral converges or diverges, or diverges. So it's saying we have to use the limit comparison test, which means I better come up with another function and if I take the ratio of the integrand with that other function, I should hope to get a limit, and that limit is either zero, is both positive and finite. And then if the integral of that other function converges, then the integral of this function should also converge. If that diverges, this should also diverge. I mean, so this test allows you to replace this integral by another integral, right? Instead of looking at the integral of f of x, you can look at the integral of g of x. And if the integral of g of x converges, then this also converges. Then if that diverges, then the other one also diverges, provided that these conditions are met. So the only reason that you ever want to look at something different than what you have is what you have may be hard, right? So if you have something hard or difficult, you certainly want to replace that by something easier and cleaner, let's say. Well, okay, so I want to replace this by something else, hopefully easier and easier to understand. And the only condition that I need is that the ratio of that integrand with this function that I want to consider, the ratio of that is finite and positive as I take x to infinity. All right, so that's what I need. First of all, let's check this integrand. It's positive, right? Well, it is positive because x is between 0 and 1 and infinity, and here everything is positive, right? So if x is in here, then this integrand obviously is positive and continuous, right? Because it's the ratio of continuous functions, well, ratio and composition and product and so on of continuous functions. So at least that part is met. I need another function, also positive and continuous on this interval, and whose ratio with this function is something that's positive and finite, as I take x to infinity, right? Okay, so let's just take a look at this function. Can I divide this function by some other function and get a finite and positive limit as I take x to infinity, right? That's really the question here. and hopefully some other simple function. All right, so let's just look at this. And brainstorm a little before doing any computations as to the fourth power. Okay, if I didn't have this 1 there, that would make this problem really easy. If I didn't have that 1 there, I would have the square root of x to the 4th, and that's x squared, and x over x squared, right? So that's just 1 over x. If I didn't have this 1, then it would be no problem at all. It's a really simple problem. It would be just 1 over x, and we know that diverges. But okay, this is not far from that, because I want to take x to infinity, right, in this ratio. I want to take x very large. So, but if x is very, very large, the denominator here, square root of 1 plus x to the 4th, this 1 is really a really insignificant thing. The bigger thing is the x to the 4th. A much, much bigger thing is x to the 4th. So for very large x's, at least, I should be able to say the following. And for large x's, that should be all that matters, because I'm taking the limit of this ratio as x goes to infinity. I should only care about large x's. So for very large x's, this 1 is very insignificant. I can drop that. So at least approximately, this ratio is more or less the same as that ratio. They aren't the same, obviously, but they're very close, because this 1 is very, 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 very small compared to the other terms. Well, okay, this is to say that this ratio, x divided by square root of 1 plus x to the 4th, for at least very large x's, is very, very close to 1 over x. Okay, so that should already give you an inkling on what the other function should be. I mean, the other function should be, in some sense, very close to this function, because their ratio is going to some constant number that's positive and finite. So they should be very much similar when x is very large. So, well, this tells you this consideration here. If x is very large, x over square root of 1 plus x to the 4th is very close to 1 over x. So this is suggesting the following. This is brainstorming on the side. This is telling me that the other function that I want to apply the limit comparison test with should be this function 1 over x. Right? So let f of x be this function that I want. The function that I'm given, and g of x be 1 over x. Well, okay. 1 over x is obviously much simpler than this thing. And I know that the integral from 1 to infinity, or 1 over x, that's divergent. So to determine whether the integral from 1 to 1 over x, whether that converges or not, that's easy, because I have an antiderivative, log x, right? And I take x to infinity, that will give me infinity. So this is divergent if I integrate g of x from 1 to infinity. If I can show that f of x over g of x gives me a finite positive limit as I take x to infinity, then the divergence of 1 over x integrated from 1 to infinity should tell me that this integral also diverges, right? So then what remains still is just to check that the limit, the conditions of the limit comparison test, they're all met. And if they are, then I'll be okay, right? So I already know that f of x is positive. So if x is in 0, 1, 0 to infinity, then f of x is positive and continuous. That's already noted before. G of x, well, is 1 over x, that's also continuous. So moreover, if x is in here, from 1 to infinity, g of x is also positive and continuous. So those conditions are met in the limit comparison test. All right, so let's continue. The most important part of the limit comparison test, I need to compare limits, right? As the name suggests. So the limit, as x goes to infinity, f of x over g of x. This limit, as x goes to infinity, let me just put those expressions in. So 1 over x, and upstairs, I have x over square root of 1 plus x to the 4th. All right. So that's f of x over g of x. All right, let's continue. That's obviously something that requires some simplification. So let's move this 1 over x to the top. So x squared square root of 1 plus x to the 4th. And I want to look at that limit as I take x to infinity. Well, okay. Whenever you see this sort of thing, it's almost a rational function. It's not a rational function because of that square root, but it's almost a rational function because you only see powers of x, right? And that's to the 1/2 power. That's the square root. So whenever you see something like that, what you always want to do is divide top and bottom by the largest power of x that you see. So upstairs, the largest power of x is x squared. Downstairs, well, the largest power of x, you have x to the 4th here, but you're also taking the square root of that. So the largest power is, well, x squared as well. So if you divide top and bottom by x squared, then what you get, x squared over x squared on top. And on the bottom, you'll get, I'm going to bring the x squared inside the square root, so that will become an x to the 4th. You see that, so it's going to be x to 1 over x squared squared plus this term divided by, again, x to the 4th. So as x to the 4th divided by x to the 4th. The reason I have x to the 4th in here inside the square root is because I brought the x squared into the, rather 1 over x squared into the square root. So I better square that if I want to bring it inside the square root. All right, so I see a lot of cancellations. So this is just 1, that's a 1. This is 1 over x to the 4th. Well, so if you take a look at that, that's much easier and much simpler, cleaner, because there's only one place where x appears. And x is going to infinity, so that little thing is going to 0, so I just have 1 over 1. Right? So that limit is just 1. And it shouldn't surprise you here, because that's precisely by design that we're getting something positive and finite, and in fact 1, because we figured it out at the beginning. I mean, this x over square root of 1 plus x to the 4th for very large x's is approximately 1 over x. So their ratio should be very close to 1, right? So this part is just to realize what we have. It's to realize the result of our brainstorm earlier. The numerator is approximately the same as the denominator if x is very large. So this ratio, unsurprisingly, is 1, right? So everything's by design here that we do get 1. All right, so then every one of the conditions of the limit comparison test is met, right? F is positive and continuous. G is positive and continuous. And their ratio as I take x to infinity, is 1, which is positive and finite, obviously, then every condition of the limit comparison test is met, so I can apply it. Let me erase the statement of the problem. So we know that one to infinity, g of x, of dx, that's 1 to infinity, 1 over x dx. That diverges. I mean, that's either what you call the p-test, or you can actually evaluate that, because an antiderivative here is log x, and you go from 1 to infinity. If you stick in infinity, you get infinity, so that's divergent. So yes, by the limit comparison test, the integral from 1 to infinity, x square root of 1 plus x to the 4th dx, that also diverges. Again, to recap, this is the integral that we wanted to determine whether it converges or not, right? We looked at it. For very large x's, it should be very much like 1 over x, because the 1 is insignificant. 1x is very large. So this is approximately 1 over x. So that's suggesting that we should take the other function with which we want to compare f of x to be 1 over x. And once we have f of x and g of x, prompted or motivated by this consideration here, we can apply the limit comparison test. Both of these functions are positive and continuous. And the limit of their ratio as I take x to infinity is 1 after this computation. So every one of the conditions of the limit comparison test is met. Right? So positive continuous for both functions, and the limit is positive and finite. So then I can conclude that either both of the intervals, both of these either converge, or both of them will converge, or both of them will diverge. And since I know one of them diverges by the p-test, or just by simple evaluation, since I know one of them converges, the other one must also converge. I'm sorry. Since I know one of them diverges, the other one also must diverge. Right? All right. Any questions on that?
Yes, there were a few comments on the chat. Do you want to address them?
Yeah,
so what
right.
does diverge and converge mean? And I like the explanation about, yeah, converge is a finite area and indefinite average.
All right. So what does it mean to converge, or what does it mean to diverge? Well, I mean, the definition here is really the following. Whenever you're looking at convergence or divergence, you're looking at a limit. So the definition here, f of x dx, that limit, well, that integral, this is defined to be the limit as n tends to infinity, the integral from 1 to n f of x dx. So to say that this converges is to say that this limit exists. And so if and only if this limit exists. Is it okay? Okay, good. Yeah, converges finite area, diverges infinite area. That's also fine, because if you are looking at an integral, that can be realized as an area under the curve, right? So if you that's your function y equals f of x, to say that this integral converges is to say that this area under the curve is finite. Right? Otherwise, it's not. Otherwise, it's not a finite area. Otherwise, it will diverge. So the finite area and not infinite area, that's better if to understand it like that. It's better if you have a positive function. If you have a positive function, then convergence and divergence, positive and negative area, they all mean the same thing. But if you have a function that's sometimes positive and sometimes negative, that could be more complicated, because you could have a positive, you could have something like that, a positive area, and can cancel out the negative area. So you can still have something that's convergent or divergent, and you may still have an area that's finite or infinite. So the situation is more complicated if you have a function that's positive and negative. All right, Zoki to say. Right. So not only does the limit need to be positive, but also finite, because if you had an infinite limit, then that doesn't really tell you anything. So the in the statement of the theorem, the limit of this ratio must be positive and finite. Otherwise, you can't use the theorem. Right. Okay.
Good questions. Yeah, I like that we get questions. Is there anything else?
All right. If not, then we'll move on to the next part.
Yes. I just put a poll there to have an idea where you're at, to have an idea if you think this is difficult or not. Remember that that's the formula of the exam we had last year, which means that you can already have 50% with only the online tutorials and the lab tests. So yeah, this is kind of extra to see. That's why it's a bit trickier, I guess. So yeah, just to have a look where you're at, and I'm gonna prepare next question. Here. Okay, so next question is about hyperbolic trigonometric functions. So in the following Maple session, you have some hyperbolic trigonometric identities that I will verify, and you have 3 of them, and I already wrote the 3 of them on the right-hand side. So the first one is cosh u, so hyperbolic cosine, so we say cosh u squared minus cosh 2u divided by 2 equals 1/2. Second one is the famous one with the hyperbolic cos and hyperbolic sine, so which we call sine. So cosh squared minus sine squared equals 1. And the last one is the kind of the double angle formula for hyperbolic functions. So sine of 2u minus 2 sine u times cosh u equals 0. Okay, so the first question is to use the definition of cosh u, so hyperbolic cosine, which you need to know, and to prove the first one. So first one is this one, cosh square minus cosh 2u on 2 equals 1/2. Okay, and remember that you can get rid of the poll. I still have 18 people who are not following, but you can get rid of the poll with the on the top right. Okay, so we need to use the definition of cosh. Up. So definition, it's of course with the exponential. So hyperbolic cosine of, well, we're going to say u here, is defined by exponential of u plus exponential minus u on 2. And I hope you remember hyperbolic sine. It's the same thing, but with a minus in the middle. Okay, so first question, we need to prove the first one, which is up there. So to prove it, we're going to start with the left-hand side and try to get to the right-hand side. So cosh square u or cosh u squared, it's just a matter of notation, but it's the same thing, minus cosh 2u on 2 equals, well, I'm using the definition, so up, I have the squared of cosh u, which is exponential u plus a minus u on 2 squared, minus 1/2 of cosh 2u, so that's now exponential 2u plus exponential minus 2u, and still on 2. Don't forget it. Okay, so you can, let's go there. I'm gonna get the 1/4 there, so that's 1/2 squared. And then you just expand the square, you get exponential u squared, which is exponential 2u, plus 2 exponential u times exponential minus u, plus exponential minus u squared, which is exponential minus 2u. Okay, that's for the first term. Second one, I still have 1/4, and this is just nothing I can do about it. Exponential 2u plus exponential minus 2u. Okay, so we can factorize everything, and we get exponential 2u. Now this one here, exponential u times exponential minus u is just 1, okay? Because it's like exponential u divided by exponential u, which gives you 1, and 1 times 2 gives me 2. Up. Then exponential minus 2u, and over there I had negative exponential 2u and negative exponential minus 2u. Okay, getting there, and then exponential 2u, I have 1 here, minus 1 here, exponential minus 2u minus exponential 2u. So basically everything cancels out except these 2, which gives me 1/2. So 2/4 is 1/2. All right, so that was the easy question, which is still worth something like 2 marks, right? So that's another technique. When you see the exam and you think you won't be able to finish everything, which might be the case. Oh, I have one person who think they would have 100%. That's nice. But all the other ones, if you don't think you'll get to the end, try to identify the questions you are the most comfortable with for the exam. For example, this one, it was pretty easy. It's an easy way to get 2 marks. Okay, so next one. Next question is a bit harder, but very interesting. So we're gonna use all of this to find an integral. So use the substitution x equals sine of u to evaluate this integral. So I'm gonna give it a name. I is the integral, indefinite integral, because we don't have limits, of square root of 1 plus x squared dx. Okay, and we know which substitution to use. Substitution. Okay, we're gonna use x equal sine, so hyperbolic sine of u. Okay, of course there's a dx, which is going to be a du, but we need to find the relation, the link between both. So if you differentiate both sides of this, dx on dx is just 1. And then on the right-hand side, if you differentiate sine, you get cosh. Okay, so cosh u. Oops. But then you need to take care of this inside function. So basically a chain rule. So times du dx. So that's what we did with implicit differentiation. And that tells me that dx, if you put it aside, equals cosh u times du, which is what we're going to use. Okay, so using this substitution, I get square root of 1 plus x squared, which is now sine of u squared, okay, times dx, and I said from my right-hand side there that dx is cosh of u du. Okay, just making sure there's no x left. Either you have everything with x, like the first line, either everything with u, like the second line. I don't want to see a mix of both. Okay, so now there's a chance that we're gonna need to use everything there. So I'm gonna just copy them up and write them on the side. Okay, so this is all the hints that we have for this question from Maple. So you see a square root of 1 plus sine squared. So we're going to use the the second one there, which says that 1 plus sine squared equals cosh squared. Equals, and here I'm using the second one. Okay, so still indefinite integral of 1 plus sine squared is cosh squared. Okay, and there's nothing I can do with this cosh u du. So it looks a bit better, especially since I have a square root squared, so I can get, well, I can get rid of it. So that's just cosh u times, well, cosh u again, and still du, which I could have written straight away as cosh u squared du. Okay, I hope you're still following. Now the integral of cosh squared is a bit tricky, so I'm gonna have a look at the help, and you see the first one there gives you a link between cosh squared and cosh 2u, which is going to be easier to integrate. So here I'm gonna use the first one. Cosh square of u equals 1/2 plus cosh 2u on u up and du. Okay, now I can separate it. The integral of 1/2 is going to be u on 2, and I'm going to have a constant here. And then the integral, I have 1/2 integral of cosh 2u, and I know that the antiderivative of cosh is just sine. So that's going to be a sine 2u on 2. Okay, and I already have my constant here. Please don't forget it. Okay, and c is a constant. Okay, so now we are almost done, but not quite. Because we managed to solve the integral, we solved it and we ended up with u, and the initial variable was x. So don't forget, the last step is always to get back to the initial variable. And the initial variable was x. We had x equals sine u, which means that u equals sine minus 1 of x. So the inverse hyperbolic sine function, which is a bit tricky, especially because here we have a 2u. Okay, so we don't really know how to take the inverse when there's 2u. So of course we're going to use something from the hint, which is here, because we have a formula for sine of 2u. So let's go back here. So this time I'm going to use the third hint. Right, so let's keep u so far, so that's 1/4. Sine of 2u is cosh, is the derivative just sine 2u. Yeah, okay, so it's the integral. So the integral of cosh 2u is sine 2u on 2. So if you look at this 2 is this one, and then I got the integral of cosh 2u, sine 2u on 2. So in the end, I have 2 times 2. Yeah, perfect. Okay, so I said that sine 2u is up. So there's a 2 again. 1/4 of sine 2u is 2 sine u cosh u. Okay, and that's it, plus c, which means, oops, I can get rid of this. So now 1/2 sine u cosh u up, and still my constant is there. Okay, getting there. So now I'm going to go back to the initial variable. Okay, so using the fact that x equals sine u, so u equals sine -1 of x. So inverse sine hyperbolic function. Okay, and this is going to be easier there. So we have sine -1x on 2 plus 1/2 of, I'm going to go step by step. So sine of sine -1 of x, okay, times cosh of sine -1 of x. Okay, and one more part. So this one, I'm just gonna keep it. Now here we have sine of sine -1 of x, and this is just x. Up. So x. And then cosh of sine -1, well, we're gonna use again the fact that there's a link between cosh and sine which is the second one, which you should actually know. So cosh of, let's say, u equals square root of 1 plus sine square of u. Okay, so this could be plus or minus, and you need to think about, and you know the cosh u looks like that, which means that cosh u is always positive, so it's plus. Okay, so I'm thinking I'm running out of battery. Let me plug it. Okay, that's better. Okay, getting that. So cosh of sine -1 is going to be, I said that cosh is plus square root of 1 plus sine squared of u, and here the u is sine -1 of x. Okay, this is all under here, and that gives you, I think we're getting there. Up. Square root of 1 plus, well, sine of sine -1 of x is just x, and everything is squared. So there's a square here. And there's something I forgot here. Anyone? Yay, thank you. Plus c. Up, plus c, and plus c. Okay, done. So I hope you followed it. Yeah, you just go step by step and see where you get stuck and which identity could help. And I think we're gonna move on straight to next one if there's no other question, which is sketching a polar curve.
All right. Any questions?
Yeah, I'm sorry, that was a bit long.
All right. Okay.
Wait, come back. Up. Okay, take a screenshot. Done? Okay. All right, moving on.
All righty. So this is going to be problem 3D. All right. All right. So it's got two parts, 2 marks each for both of the parts. So first part, I want to sketch this curve. So R, so the polar curve. So R is defined as a function of theta, and it is 1 plus sine theta. So that's what we have. Well, okay. So before plotting the polar graph, let's just take a look at this function first as a function on the r theta plane. So if it's on the r theta plane, then it's a much easier problem. So sine is this oscillatory function, right? It goes like that. So that's y equals sine of x. Okay, so pi, 2 pi, and 3 pi, and so on. So negative pi. That's what sine looks like. Well, the only difference between this and sine is that there's a 1 added to it. So this entire graph is just shifted upward by 1 unit. So that's 1 there. Oops, that's 2 up there. So everything here is shifted upward by 1 unit. So and so on this side as well. All right. So that's 0. That's 1. That's 2 up there. Right? So that's r equals 1 plus sine theta on the theta r graph. So that's pi here. That's pi over 2. That's pi. That's 3 pi over 2. And that's 2 pi. Sine has period 2 pi. So 1 plus sine also has period 2 pi. It's just merely shifted upward by 1 unit. Okay, so, and that's pi over 4 over there. That's 3 pi over 4, and so on, right? That's 5 pi over 4. That's 7 pi over 4. 7 pi over 4. All right, so let's let's move on. All right, so on the polar graph, it's going to be a little bit more complicated because this vertical axis is going to become the distance to the origin. Yeah, go ahead.
Isn't the 2 pi supposed to be a bit closer to the left?
To the left, what do you mean? This here?
Yeah.
Yeah, right. So that's not 2 pi, yeah. So 2 pi is here,
Yeah.
and that's 7 pi over 2. 7 pi over 2. All right.
Yep. All right. Yep.
All right, so once I'm on the xy plane, this becomes a little bit more complicated because the horizontal axis becomes the angle, and the vertical axis becomes the origin, becomes the distance to the origin. So let's just pick out a few points and see what we get, right? Because we do have a bunch of sample points. So the positive x-axis, that's theta equals to 0. That's theta equals to pi over 4. That's theta equals pi over 2, right? That's theta equals 3 pi over 4. That's theta equals to pi, and theta equals to, let's see, 5 pi over 4, 3 pi over 2, right? And 7 pi over 4. All right, so let's just take a look at these angles, and then we'll pretty much be able to sketch a graph. All right, so when theta is 0, r is 1. Right? So that's 1, 2, that's 1. So let's say that's just 1. And at pi over 4, this point, that's, well, sine of pi over 4 is 1 over square root of 2. So, but 1 added to it is just 1 plus square root of 2. Right? 1 plus 1 over square root of 2. So it's clearly larger than 1. So I'm going to be here somewhere. Right? So that's this distance. That's going to be 1 plus 1 over square root of 2. And when I'm at pi over 2, my height is going to be 2 now. So if that's 1, and that's 2, so I'm going to be up here now. And what about 3 pi over 4? Well, 3 pi over 4 is completely symmetric to pi over 4 about pi over 2. So I'm back down here again. That's 1 plus 1 over square root of 2. And when I'm at pi, I'm back down to 1. So so that distance here is 1 plus 1 over square root of 2. When the angle is pi, I'm back down to 1 again. All right, so let me just make sure this looks more or less as it should be. All right, and okay, so at 5 pi over 2, I'm below 1 now. At 5 pi over 2, this is 1 minus square root of 1 over square root of 2. Right? So that's clearly less than 1. So that's going to be here somewhere. So 1 minus square root of 2. And at 3 pi over 2, I'm actually at the origin now. And when I get to 7 pi over 4, that's symmetric to this point. So I'm once again at 1 minus 1 over square root of 2, which is smaller than 1, obviously. And of course, when I get back to 2 pi, I get back to 2 pi, I will have completed one complete revolution around the origin and gotten back to 1. All right, so what remains is to connect the dots, if you will. So right, this is a little bit inside. So this, I need to get back to 0 at pi over 2. I mean 3 pi over 2, and back out. So in fact, I should probably use a different color. Use red here. Yeah, right. Precisely. So it's sort of like the cross-section of a peach, right? That's basically the picture. Well, because at 3 pi over 2, r is precisely 0, right? Because at 3 pi over 2, sine is -1, so 1 plus -1, that gives you 0. So at 3 pi over 2, r is 0, so you're back to the origin, right? Good. All right, so let's keep that picture in mind. That's basically part 1 of the problem. Any questions on part 1? Basically, you pick out some sample points. Since you won't have Maple with you, during your exam, you basically pick out some sample points. And usually these 8 points are enough to give you an idea of what this graph looks like. All right, so in fact, let me keep that graph here for part 2. So it's 2 up here, and 1 -1, so that's 0 down there, right? The graph looks like that. That's part 1.
So I just put a poll together to ask if they wanted to go over time, because otherwise we're running really out of time. And they said yes. So I think we just go, yeah, maybe, yeah.
Yeah, maybe
10,
half an hour more. That's
10, 15 minutes. Yes.
Yeah.
Thanks.
Yeah. All right, so let's look at part 2. What you'll require is some computation. Well, part 2. So we're looking for places where the curve has vertical tangent lines. So find the coordinates. Of the points on the curve with vertical tangents. Coordinates of the points with vertical tangents. All right, so if you simply look at this picture, where would you have vertical tangents? Well, if you are to draw tangent lines on this curve, it seems that around these 2 points, because of this symmetry here, around these points you should have vertical tangents, right? Well, then it still remains to figure out what those 2 points are, but simply from the picture, that's where I should expect vertical tangents. And maybe also here, in fact, because if I come into 0 there, to the origin there, it seems as if I may end up having vertical tangent lines. So let's take a look at those. Right. Okay, so let's take a look at those. So vertical tangents means that the slope of the tangent line is infinity. And so to compute the slope of the tangent line, you need to differentiate. So vertical tangents, that's basically the same as saying dy dx is plus or minus infinity, right? That's what that's saying. Well, if dy dx is equal to plus or minus infinity, then we better figure out where those things are. So dy dx is, well, there are a couple of ways of computing that, which is really the same way. So it's either you can write y as a function of theta and differentiate with respect to theta divided by x prime with the derivative of x with respect to theta. So this is, let me write it this way. So dy d theta divided by dx d theta. Or your lecturer might have actually given you a formula. So it is r cosine theta plus dr d theta sine theta. Then negative r sine theta plus dr d theta cosine theta. So either way, you can compute dy dx. And since I want to know where this is positive or negative infinity, that basically amounts to 1 is the denominator 0. Right? More or less, the numerator could also be 0. Right? If you have 0 over 0, then it gets more complicated. So at least among the possible candidates are the places where the denominator is 0. If you have a 0 denominator, then you can possibly get infinity as the ratio. If the denominator is not 0, then the ratio is not going to be 0. All right, so let's just do that. So y is, well, because of that relation, it's r cosine theta, r sine theta, because of the formula between the Cartesian coordinates and the polar coordinates, and x is r cosine theta. Right? So I want to differentiate this with respect to theta, and differentiate that with respect to theta, and see whenever when is the denominator 0. So r, I'm given, well, from the very beginning, r is 1 plus sine theta. Right? So let's put that in. So r, 1 plus sine theta, and x is 1 plus sine theta, cosine theta. Right? All right, so let's just differentiate those things. So dy d theta is, well, okay, the product rule. So the derivative of the first, which is cosine theta, times the second, sine theta, plus the first times the derivative of the second. So plus 1 plus sine theta cosine theta. Got it? All right, so let's see. Well, what is that? It is, so cosine theta plus twice. Well, let me pull the cosine theta out. So then it's 1 plus twice of sine theta. That's what the derivative of y with respect to theta is. Right. So so the dy dx is, as someone else answered, because we want to we are in the xy plane, right? So to get vertical tangent lines is where we're basically considering the slope of lines in the xy plane. So dy dx, that gives me the slope of lines in the xy plane. So that's why we want to compute this dy dx, because the xy plane is where the picture is. Well, okay, so dy dx. Well, one way to compute that is to look at dy d theta divided by dx d theta. It's that's basically how the chain rule works. So you can either compute that or just use this formula, which you might have seen in your lecture. So in order to compute dy dx, this derivative, which gives you slopes of lines in the xy plane, compute dy d theta, divide that by dx d theta. Actually, if you make that computation, if you go through that computation, that's the precise formula you will get. So I'm writing y as a function of theta and x as a function of theta and differentiating. Right? That's what I'm doing. Yeah. So dx d theta. Then, well, I need to differentiate this with respect to theta now. So the derivative of the first, which is cosine theta, multiplied by cosine theta, so I get a cosine squared theta, plus the first times the derivative of the second, which is minus sine. Good. So it is cosine theta minus cosine squared theta, and I have a minus sine squared theta, and I have a minus sine theta. All right, so let me put the formula here so that it's more more prominently displayed. So dy theta is so cosine theta 1 plus sine theta, 2 plus sine theta, and dx d theta. Well, and put on the second line, so dx d theta is cosine squared theta minus sine squared theta minus sine theta. Well, okay. All right, so remember, this is dy dx is dy d theta divided by dx d theta. I want to know where is dx d theta 0, right? Because I want this ratio to be infinity. That's to say that the denominator better be 0, because otherwise there's no way to get infinity. So the denominator has to be 0, so dx d theta must be 0, so dx d theta is here. It's difficult to tell where this function is ever 0, because you got sines and you got cosines. Whenever that happens, what you want to do, it's better to have only sine or only cosine, because then you'll have a polynomial in sine or cosine. That's much easier to deal with instead of just sine and cosines. So whenever that happens, you want to make a you want to either have only sines or only cosines. So cosine squared is 1 minus sine squared. So this is 1 minus 2 sine squared theta minus sine theta. Yep. So cosine is 1 minus sine. Rather, cosine squared is 1 minus sine squared. So this 1 minus sine squared together with that sine squared, so you get a minus 2 sine squared. Minus sine squared is still there. So now that's only in sine, which will make things easier for the following reason. So it's 1 minus sine theta minus 2 sine squared theta. I can factor things now. This can be factored in the following way. So negative sine theta plus 1, then 2 sine theta minus 1. Okay, so to examine where is dx d theta 0, it's enough to examine where is this 0 and where is that 0. Those are your only possible candidates. If this is never 0, that means the denominator here is never 0. That means you will never get positive or negative infinity as a ratio. So wherever these things are 0, those are the only places where you can have vertical tangents. All right, so just continue here. All right, so where is this 0? Well, this is 0 when either one of these factors is 0. So dx d theta equals 0. That tells me either this is 0 or that is 0. Right? So sine theta is -1, which means the first factor is 0, or the second factor is 0, or is, well, a half, right? All right. So that gives me a bunch of candidates. So where is sine theta -1? Well, so between 0 and 2 pi, sine is only -1 at 3 pi over 2, right? So theta, this tells me theta is 3 pi over 2. Well, where is sine 1/2? Well, it's 1/2 here, right? At 2 places. That's pi over 3. No, not pi over 3. That's pi over 6, rather. That's where sine is a half. Pi over 6 and 5 pi over 6. That's where sine is a half. So I got 3 possible places. So theta is pi over 6, or theta is 5 pi over 6. All right. So, well, does that confirm, or is that consistent with our original observation? Well, okay, it seems as if this point should be pi over 6. That point should be 5 pi over 6. And this point at the origin, that's 3 pi over 2, right? So at least all 3 possible candidates are there. All right, so we're on the right track at least. All right, so let me erase that. All right. So let's examine all 3 of these. I erase dy d theta. Dy d theta is cosine theta 1 plus 2 sine theta. All right. So at those 3 places, so theta equals pi over 6, theta equals 5 pi over 6, and theta equals to 3 pi over 2. 3 possibilities. If I got something non-zero divided by something that is 0, then I certainly get infinity. Then I'll have a vertical tangent. So remember, dy dx is dy d theta over dx d theta. So if I get a 0 in the denominator and something non-zero in the numerator, then I certainly get a vertical tangent. Something non-zero divided by something that is 0. But if I get a 0 in the denominator, but also a 0 in the numerator, then things will become more complicated. So let's just take a look at the top, right? So dy d theta is this formula here. So at this point, theta is equals to pi over 6. Dy d theta is cosine pi over 6, 1 plus 2 sine pi over 6. Whatever that number is, it's definitely non-zero. Right? This is only, cosine is only 0 at half multiples of pi. And let's see, what does this need to be? This needs to be negative a half. Sine needs to be negative a half in order for this to be 0. Sine is only negative a half of after pi. So that's never going to be 0. And at 5 pi over 6, cosine 5 pi over 6, 1 plus twice of sine 5 pi over 6. Well, it's the same consideration. Cosine is not 0 there because cosine is 0 at half integer multiples of pi. And that's not going to be 0 either because in order for this factor to be 0, sine here needs to be negative a half. But sine is only negative a half once you pass pi, but 5 pi over 6 is still smaller than pi. So that's not going to be 0. So at least for these 2 points, we can be sure that I do have vertical tangents. Okay. All right. And that's consistent with our earlier observation, right? So that point there, that should be theta is 5 pi over 6. Right? And that, oops, that's not 5 pi over 6, that's pi over 6. Over there, that's theta equals to 5 pi over 6. All right. Okay, so let's look at that point there. Well, I won't discuss this in its greatest possible detail, but at 3 pi over 2 dy d theta, what is that value? Well, there's going to be a problem here. Because if you look at dy d theta at pi over 3, so it's cosine 3 pi over 2, right? And 1 plus sine, 2 sine 3 pi over 2. Cosine is 0 at half integer multiples of pi, and this is precisely one of those. So this is going to be 0. Right? So at 3 pi over 2, you actually get 0 over 0. Let's zoom in to that point and see what's actually happening. So at 0, this is 3 pi over 2. What's happening is the following, right? So if you zoom in to the origin, that's the picture you'll see. One way to think about this is that you actually have a sharp turn there. You have a cusp there. Whenever your graph has a sharp turn, like with the absolute value function, whenever a graph has a sharp turn like that, that means the function is not differentiable there. If it's not differentiable there, then it won't have a tangent line. If it won't have a tangent line, then it certainly won't have a vertical tangent line. Right? So, yeah, okay. So the well, so dy dx does not exist at theta equals to 3 pi over 2. So hence no vertical tangent line there. There's no tangent line at all, therefore no vertical tangent line there. I mean, if you're interested in exploring this, 3 pi over 2, because you do have 0 over 0, you can actually explore, apply L'Hopital's rule or something. So S theta goes to 3 pi over 2 dy d theta over dx d theta. This limit does not exist. But the two one-sided limits exist. So as you take theta to 3 pi over 2, from either the positive or from the left or the right, you actually get one-sided limits. So if you come in from the left, you get positive infinity. And if you come in from the right, you get negative infinity. So it's exactly negative positive infinity. So the limit, the two-sided limit does not exist. But if you only look at one from the left or the right, you do have limits, but the two one-sided limits exist, but the limit itself does not exist. So that limit doesn't exist, which tells you that the function is not differentiable there, which tells you that there's no tangent line there, which means there is no vertical tangent line. So there are only two places where you get vertical tangents, and those are the places, right? All right. Any questions here? Vertical tangents at pi over 6 and at 5 pi over 6. Any?
Yeah, that was a long, yes. It's always, polar curves is always long.
All right.
But yeah,
okay. So let's.
We just need the coordinates now. Well, that's what you did with the polar plot in the XY plane.
Right. Yeah. So if you.
Okay. Because they asked find the coordinates of the point. That's fine. You said it happens for theta equals, what did we find? Pi on 6 and 5 pi on 6. That's enough for the answer. Maybe you could find the radius. I think we need to move on.
Yeah, so it's basically R of pi over 6 and R of 5 pi over 6 at this point, right? So it's 1 plus sine of pi over 6 and 1 plus sine of 5 pi over 6. Right? And once you have R, you can figure out X and Y. And right, so if you know what R is and you know what theta is, you can figure out X and Y. Right?
Yeah.
And also, you can just leave it in the polar coordinates as well, because it's asking for the coordinates, and if you give the polar coordinates, that's completely fine.
Yeah, I agree. Any other? Okay, 5 seconds. Okay. So last one, I'm not gonna do it because we are running really out of time. But I'm just gonna show you my answer. So the last question here is about the definition of the limits. Show us the working. Yeah, there it is. So you have a function, and we actually tell you the definition of the limit, which you already know. So limit at infinity states that for all positive epsilon, there exists a real number m, such that if x is greater than m, then the distance between the function and the limit is less than epsilon. Okay, so we need to use this definition to prove that the limit of cos x as x tends towards infinity is not 0. So the idea here, remember, it's always easier to prove that something is not true in general. So the definition says that for all positive epsilon, you can find a number m. So we're going to prove that, we're going to show that, well, I can find at least one epsilon for which this is not true. And that's enough to prove that the definition, that it doesn't apply here. Okay, so let's go through that. So this is a function, cos x, okay? So for the limit of cos x, you need absolute value of h, well, cos minus 0. And you know that this is always less than or equal to 1. So the idea is to find at least one epsilon such that there is no real number m for which whenever you are greater than m, the absolute value of cos x is less than epsilon. For example, you have many examples because you know that absolute value of cos x is here and it's going to oscillate basically forever, right? It's going to do this kind of things. Sorry, that looks awful, but like forever. So you cannot find a m such that this is always going to be less than or equals to an epsilon if you choose epsilon less than 1. Okay, because this is always oscillating between 0 and 1. So if you choose epsilon here equals 0.5, you'll see that you will never be able to find x or m large enough such that this function is going to be below the line y equals 0.5. Okay, so that's the idea. So have a look there, and yeah, maybe take a screenshot or I don't know. But I think, and if you have questions, please ask them straight away. Otherwise, we're gonna finish the session here. Any answers? Answers to what? That's it? Yes, that's it. Remember, we're trying to prove that something is not real, that is not working. So you just need to find one counterexample. If you find one counterexample, if you find, for example, epsilon equals 0.5, you're showing that there is no m such that if x is greater than m, absolute value of cosine is less than this epsilon, it's enough to show that this is not true for all positive epsilon. All right. Okay. This one was worth 2 marks. Yep. All right. So if you have more questions, quickly, or consultations. So don't forget the consultations. Thank you for all your questions and participating. It was really good to have a bit of interaction as much as we can. And otherwise, I'm going to tell you good luck and yeah, see you sometime. Lee, do you want to say something?
Yeah, that's it. Thank you for coming and good luck with everything. And I'll stop the